Hi everybody! So to start off this chapter before we go into the new material, I wanted to make sure that you guys were comfortable with using units to describe your answers. A big part of what we're going to be doing in this chapter is interpreting our answers in the terms of a context. So to do that, we're going to need to be able to use units properly. Throughout the next chapter, we are going to be applying our calculus ideas to real-world applications. For most of the questions you will be asked, you are going to be required to explain the meaning of your answer in the context of a problem using correct units. Now, when a question asks you to explain the meaning of your answer in the context of a problem, there are three components to that explanation. The first part of the explanation needs to be stating what you calculated or measured. The second part of the explanation needs to include a description that uses vocabulary. So for example, if you're finding a derivative, that vocabulary might include the word increasing or decreasing, because derivatives tell me if a function is increasing or decreasing, or if they, in other words, if they have a positive or a negative slope. And the third component needs to be the value you found and the units that are appropriate. Now we're going to practice writing some of these sentences today. We're even going to do a few calculations together to review some of the things that you might be able to do on your calculator or by hand. So let's start with derivatives. Now derivatives were a big topic of first semester. Earlier this year, we used units to describe our answers in the context of position, velocity, and acceleration problems. As a reminder, one of the things we might have said earlier this year is that it is speeding up, or an object is slowing down. So in this context, what does this mean? Slowing down. There we go, slowing down. Talking and writing at the same time are sometimes a challenge for me. What we're going to look at now is the ways that derivatives are used in other contexts and how you would explain answers outside of simply a position, velocity, and acceleration context, which we theoretically are already comfortable with. So let's review. When we find a derivative, what we are really calculating is the instantaneous rate of change. So, one of the vocabulary words that you're going to use a lot here in the descriptions is rate, because a derivative is a rate. Or another way to think about this is the slope. In order to determine the appropriate units, which is the third component of a good explanation, the appropriate units can be determined by thinking of a slope as a ratio. When we were younger, we thought about it as rise over run. And we can think about the units in a similar way to help use the units to analyze what it is that we're calculating. For example, now the first one we're going to do here, we do not have a calculator. The second one, we're going to use our calculator. This one says the height of a tree at time t is given by a twice differentiable function h, where h is measured in meters and t is measured in years. Selected values of h of t are given in the table. Part A says use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. Now there are two steps sort of to this process. The first step is you need to actually do the calculations, please. So let's start with that. So if it says here we need to actually use the data to estimate this derivative, then step one would be calculating h prime of 6. Now normally to find a derivative, we would take our function, whatever equation we had, we would take the derivative and then plug in our value. One of the reasons that we use the word estimate here is that we don't actually have a function. However, to estimate a derivative, since this is just a slope, we can use our regular old slope formula from way back in Algebra 1 and use the data in the table to estimate it. Since the number 6 falls between 5 and 7, we would calculate the slope between 7 and 5 by doing h of 7 minus h of 5 over 7 minus 5, which means I would do h of 7, which is 11, minus 6 over 2, and I would get 5 over 2. Then it says, so that's kind of part one, we found our value. Then it says using correct units. Now remember, units are also a big component of our explanation. So let's figure out the units before we work on explaining the meaning. So the units here of the h values, the top values would be meters, and the units here of the bottom values would be years. In other words, our overall units would be meters per year. So our units would be meters per year, which again is helpful to think about this as rise over run or a ratio. It should be something per something else. Now let's work on the second part of this question. So using correct units, interpret the meaning of h prime of 6 in the context of the problem. Let's start with the first part of our explanation, which should be, what did you measure? We were calculating the height of a tree at time t. That's the data that was given in the table, and we were finding the slope. So, what did we measure? The height of the tree. Okay, so that's kind of, we're copying it out of the problem. What did we measure was the height of the tree. Describe it using a vocabulary. So the height of the tree was doing what? Well, we found the rate, which was a positive number. So one of the ways we describe a positive rate is we say was increasing at a rate. So we're using increasing at a rate to describe. Rate meaning we found the slope, increasing means the answer we got was positive. At a rate of, and now we need to give the value and give units. At 5 over 2 meters per year. So what were we measuring or calculating? The height of a tree. What did we find? Since the slope was positive, it was increasing at this rate. If our slope had been negative, we would have said that the height of the tree was decreasing at this rate. Of 5 over 2, here's our specific value, meters per year. Here are our units. Now we're going to do a similar problem where we are going to use our calculator and kind of review that our calculator can be used to find derivatives as part of this process. So when a certain grocery store opens, it has 50 pounds of bananas on display. Customers remove bananas from the display table at a rate modeled by this function. So this function is the rate at which customers remove bananas. Where f of t is measured in pounds per hour, so they're giving us some units here to work with. And since we're going to need the units later, we've got pounds per hour for a certain number of hours after the store opened. Find f prime of 7, so that's going to be step 1. And then, using correct units, explain the meaning. Now in this case, since we have a calculator, we can and we should use our calculator to find that derivative. So I'm going to go to math option 8, which is finding the derivative on my calculator. You may remember that from much earlier this year. I'm going to type in the x for d over dx, and I'm going to type in my function 10 plus 0.8x sine of x to the third power divided by 100. And the value that I want to substitute is 7. So step 1, find the value. And we always use 3 decimal places. Now let's think about the units. So before we start explaining, let's think about the units in a similar way to what we did here. We started off with our y values being measured in pounds per hour and our t values being measured in hours. Just like we took these y value units and divided by the x value units, we're going to do the same thing here. So we're going to have pounds per hour per hour. In other words, we're doing the rate of the rate. You may want to kind of mentally compare this to acceleration. Now, we're not using the word acceleration here. This isn't a position velocity acceleration problem, but think about this as almost like the second derivative, because we started with a rate initially, and then we did the derivative again. Now, for our explanation, we're going to start with what are we measuring? We started with measuring the rate at which customers remove bananas. So we would say the rate at which customers removed bananas. So what did we measure? What was it doing? Well, when you find a slope, you're going to be looking at increasing or decreasing. Is your slope positive or negative? Since we got a negative number here, we would say was decreasing at a rate of, and now we're going to give our actual calculated value, of 8.119 pounds per hour per hour. Now you'll notice, although my value was negative, I did not say a negative here, because the word decreasing means our rate was negative and here's what it was. If you put the negative here, it's kind of like having 2 negatives. You have the decreasing negative and another negative, and it doesn't make any sense. So if you'll pay attention to the explanations here, the setup is kind of the same. What did we calculate? Using the word increasing and rate or decreasing and rate, because we're finding a derivative, which is a rate, and decreasing tells me my rate was positive or my rate was negative. Decreasing or increasing. And then here's what I calculated, and here are my units. Let's look at another example now where we're going to look at units with integrals. When we find an integral, we are really finding the area between a curve and the x-axis. So in order to determine appropriate units, it is helpful to think about this as an area problem. For example, if I knew that on this particular problem, the y values of my function were measured in liters per hour, and the x values of my function were measured in hours, then when I find the area, the units are going to be liters per hour times hours, because area is usually base times height, which means the hours would cancel and we would just have liters. In other words, if you integrate a rate function like this, if you find the area, you're going back to the original amount of stuff that you started with, the liters. Now we're going to use our calculator on both of those, just simply for number 1, arithmetic, and number 2, because we can also do integrals on our calculator. So let's read the directions. Water is removed from a tank at a rate modeled by this amount. So what are we measuring? The water that's being removed from a tank. Where r is differentiable and decreasing, selected values of r are shown in the table. At time t equals 0, there were 50,000 liters of water in the tank. Use a left Riemann sum with 4 sub-intervals indicated by the table to estimate the amount of water removed. So this first part is just doing a calculation. Use a left Riemann sum to estimate the total amount of water removed. So for a Riemann sum with 4 subintervals, I like to show my work by drawing 4 spaces. My first interval would go from 0 to 1, then 1 to 3, 3 to 6, and then 6 to 8. I'm going to use the left side to find my height. The height would be 1340, 1190, 950, 740. So I would do 1 times 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740. And if I do that on my calculator, I get 1340 plus 2 times 1190 plus 3 times 950 plus 2 times 740, and I get 8050. Now we already know that we used this to estimate the total amount of water removed. So you'll notice that this problem does not say explain your answer, because they already told us this is giving us the amount of water removed. We added up all of these liters of water. So what units would we use? Well, if we think about the units here, we're doing liters per hour times hours. So we would, and you can do this on the side, or you could kind of do this in your head, liters per hour times hours, we would just be left with liters. In other words, if this is a function that tells me the rate at which water is removed, so this is the rate at which water is removed, then when I integrate, I just get how much water was removed in liters. Now we're going to do a problem. It's the same actual setup as the second problem on the previous page. When a certain grocery store opens, it has 50 pounds of bananas on display. The customers remove bananas at a display table at a rate modeled by this function. So once again, this is the rate at which customers remove bananas, measured in pounds per hour, and t is the number of hours. Find the integral from 0 to 2. Give your answer using correct units. So, one thing that we haven't talked much about is that just like you can find a derivative on your calculator, you can also find an integral. If you go to math again and go to option 9, you'll notice that it brings an integral to your screen. Now I want to integrate from 0 to 2. And then I'm going to type in this equation. So 10 plus 0.8x times sine of x to the third divided by 100. Oop, I don't need that parentheses. I don't need that in the exponent either. And we want this dx. Did I make that same mistake earlier? Oh my gosh. No, I was good. Okay. All right, so let's try this again. Sorry, I just wanted to make sure I didn't screw up the problem on the other page. Math option 9, 0 to 2, 10 plus 0.8x sine of x to the third divided by 100 dx. And we get that it's 20.051. So the first part of this question is find this integral. Okay, well the integral from 0 to 2, f of t dt, would be 20.051. Now it says give your answer using correct units. So we know that f of t is measured in pounds per hour, and t is the number of hours. And again, you can do this kind of on the side, or you can do this in your head. If you do pounds per hour times hours, your answer is just going to be pounds. Now, although it doesn't say it here, I want to show you kind of how you could interpret this answer. So what you would say here when you interpret this answer is the same three components. What did we measure? What does it mean? What are the units? If you integrate pounds per hour and you get pounds, then instead of getting the rate at which customer removed bananas, you're getting how many bananas were removed. So the integral from 0 to 2, f of t dt equals 20.051 means 20.051 bananas were removed Now we need to give the specific time interval here because it's from 0 to 2. In the first 2 hours after the store opened, and so now we've said, here's what we calculated, here's how we have to say measured in pounds. Sorry, I got ahead of myself. We said, here's what we calculated, here's how we measured it, and then here's kind of the time interval over which it happened. In the context of this problem, it's in the first 2 hours. All right, thank you guys so much for watching. I hope this kind of makes sense why the units work out the way that we do, because we're going to be using units throughout the whole unit. See you tomorrow.